So how do we describe these quantum mechanically? Right. Well, in valence bond theory, we said it's going to be overlapping atomic orbitals in a bond. Right. Our orbitals can be hybridized. Right. So here we've got some carbon, right, and it's going to be hybridized to be like this guy's going to be sp2 hybridized, and this guy will be an sp3 hybridized. But our electrons are basically all sitting on that carbon, and one might share this way and one might share that way. But they're still localized pretty much on those. Molecular orbital theory. In molecular orbital theory, atomic orbitals are going to combine to form new orbitals, which are spread out over the entire molecule. Right? Orbitals which belong to the molecule as a whole. And this is a much more sophisticated model. We're just going to go scratch on the surface of this. We're going to look at some very, very simple models like diatomic ones. We're only looking at molecules that have 2 atoms because the math that gets into this gets real difficult real fast, because now you're combining wave equations over 4 or 5 different atomic centers in even a simple molecule, and it just gets computationally pretty intensive. There are programs out there that do that. Gaussian is a good one. I think there's one called Avogadro that does a decent amount of molecular modeling like this, but it's tricky stuff, right? So we're just going to cover it on a very simple, almost superficial level. I will expect you to know how to do some of the orbital diagrams that we will see. You will definitely, if you continue with chemistry, go into this in a little bit more detail, especially if you start taking inorganic chemistry. So valence bond theory works great for organic, right? But molecular orbital theory works better for inorganic. Right? So organic just means chemistry with carbon. Inorganic means everyone else, right? So anything that's not going to be carbon obsessed, right? So our functions, remember, they're mathematical functions. They can be either added or subtracted. So I've got some mathematical function for blue and some mathematical function for the red line, and I can add them together. So if I got 5x and x, I can add them together and get 6x, or I could subtract them, right? And I could take 5x minus function y2, and I can get 4x, and I can get a difference. Those functions do not need to be on the same origin, though. Right, so we had these 2 functions. They were both centered at the same origin here, but they don't have to be, right? I can do this on y and y prime, and I can sum those up, and I can still get a sum. Okay? Or I could get a difference. And that's what we're doing when we do our molecular orbital theory. So you can kind of think of, and this is a vast oversimplification, you can think of your valence bond theory and coming up with our hybrid orbitals as doing this, where we've got some sort of atomic center. What's happening on this carbon? Or what's happening over here on this oxygen? And we'll look at its hybridization. When we're doing our molecular orbital theory, like this might be a carbon and this might be the oxygen that it's bonded to, and then over here we might have the hydrogen, and that might be y double prime, right? So you can shift that center around, right? So just like we did with those functions that were linear, we can do that with wave functions instead. So our waves can either reinforce themselves, right? So here we've got 2 wave functions, one for each nucleus, and the waves can reinforce each other, and that can be constructive interference, or we can have destructive interference, right? Where we've got the waves canceling each other out and a node of 0 electron density appearing between the 2. Our atomic orbitals were a wave function whose square gives the probability of finding an electron within a given region of space in an atom. And our molecular orbital is a wave function whose square gives the probability of finding an electron within a given region of space in a molecule. So our molecular orbitals are wave functions resulting from adding or subtracting atomic orbitals or wave functions. And we can represent this pictorially. Right, so if we got 2 hydrogens, right? The hydrogen's coming in with a 1s electron, and this guy's coming in with 1s electron. I can combine them into a new orbital that incorporates both of those. So if I look at those 2 wave functions, right? I've got my atomic orbitals. My hydrogen's got an s, and this hydrogen's got an s, and I can combine them constructively, right, and get some nice overlap, or destructively and get this node here. Right, I'm going to either add them or subtract them together. Right? The adding is going to be lower energy. That's going to fill first. And we're going to call this a bonding orbital. And we've got an anti-bonding orbital, which is higher energy. And we're going to give the following symbolism. This bonding orbital is going to be a sigma orbital. And then this anti-bonding will be a sigma starred orbital. Notice we still have two orbitals. Over here, we've got two orbitals. So we're kind of doing a little bit of conservation, right? When we look at that constructive interference, we've got high electron density happening between the two nuclei. Right? Lower energy and more stable than the atomic orbitals that were added together to make them. So if we looked at an energy diagram, right, we would have our hydrogen's s orbital from this guy, and then here's the other hydrogen. He'd come in with his s orbital, and we would end up with a sigma orbital that would be lower in energy. Right, and sometimes you see a little dashed line indicating that where these guys are coming from. In doing the difference or destructively interfering with these guys, we're going to have a low electron density between the nuclei. Right, we've got a node in between them. These are higher energy and less stable than the atomic orbitals that were subtracted. Right? So if here was our hydrogen's s orbital and here was this other hydrogen's s orbital, right, we would have an antibonding orbital, or sigma starred, that would be higher in energy. So our complete diagram is going to have both of those. Right? We're going to have both a bonding, sigma bonding, and a sigma starred antibonding. Right? And there is a node, a planar node, that occurs in between these. Right? The electron probability of both molecular orbitals is centered along the line passing through the two nuclei. MO1 is the greatest electron probabilities between the two nuclei. On MO2, the greatest electron probability is on either sides of the nuclei. MO1 and MO2 are referred to as the sigma molecular orbitals. In the molecule, the only molecular orbitals available for occupation by electrons. So MO1 is lower in energy than the 1s orbitals of the free atoms, while MO2 is going to be higher in energy than the 1s orbitals. A bonding molecular orbital is going to be lower energy than the atomic orbitals, so you can imagine those electrons as kind of running downhill or flowing downhill into that lower energy state, which is that bonding orbital that says, hey, I want to be occupying space in between my two atoms. If I'm in between my two nuclei, I've got a bond. I'm sharing electron density between the two. So that's how our bond is forming. Our antibonding molecular orbital is higher in energy than the atomic orbitals from which it was composed. Each molecular orbital can hold two electrons with opposite spins. Right? So when we combine these, we've got the sigma or the s orbital from one hydrogen and the energy of the atomic orbital from the free atom on the other side, and we will form both an antibonding, higher energy, destructive interference, and a bonding, lower energy orbital that we call the bonding orbital. So you've got a bonding and an antibonding, a sigma or a sigma starred. Right? The MO model is physically reasonable. In bonding molecular orbitals, electrons have a higher probability of being between the two nuclei. And we do an experiment, and that's where we see them. In antibonding molecular orbitals, electrons are mainly outside the space between the nuclei. The labels on the MOs indicate their symmetry, the parent atomic orbitals, and whether they are bonding or antibonding. Right, so our symbology is going to tell us, right, some of where did these molecular orbitals come from. The molecular electronic configuration can be written in a manner similar to atomic electronic configuration. So just like we had our off-bow principle where we have electrons filling up from lowest to highest energy states, we're going to do something exactly the same, except instead of looking at atomic orbitals, we're going to look at molecular orbitals, right? So the concept is really similar. The number of orbitals you will notice is conserved. The number of molecular orbitals will always be equal to the number of atomic orbitals that we use to construct them, right? So here we have our sigma and our sigma starred, our electron from our s orbital from the first hydrogen, and the electron from the s orbital of our second hydrogen have places they can go. Are they going to go into this excited one? Not without a decent bit of energy. They're going to want to be in this lower energy conformation. So you can imagine these guys as drifting down this way. It's going to release some energy when it does that, and it forms that bond, right? So remember when we said bonds are formed, they release energy, right? So here you can see that it's going from a higher energy to lower energy. That energy has to go somewhere, it gets released. If I want to break this bond and move these two hydrogen nuclei apart and break that bond so they each have one electron, well, now I've got to reverse that process. It's going to take energy, right? Breaking bonds takes energy. How do we know if something is going to be reasonable, though? We need a tool, and that's called bond order. Our tool is bond order. It refers to the difference between the number of bonding electrons and the number of anti-bonding electrons divided by 2. And 2 is considered, given the fact that the electrons are going to take the form of pairs. So our bond order is going to be the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So in our the larger the bond order you've got, it's generally related to the greater bond strength. So in our example for an H2 minus ion, right, our hydrogen minus is going to come in with an extra electron. So I've got 2 electrons on the left, 1 electron on the right. Right? One of these is going to go down. We're going to end up filling this up just like we would with our Aufbau principle. So we've got 2 energy levels here. We'll do 1, right, 2. And then we got a third one that's got to go into this anti-bonding orbital. So our bond order is going to be 2 minus 1, right? And it's going to be 1/2. 2 minus 1 over 2, which is 1/2. There you go. Fix that. Homonuclear diatomic molecules are ones in which we combine 2 atoms of the same type. So something like N2O2, H2, F2, Cl2. Those are homodiatomic, same nuclei, atomic, 2 atoms molecules. These molecules are composed of 2 identical atoms. The valence orbitals significantly contribute to the MO, molecular orbitals of a particular molecule. Our electron probability in such molecules is high above and below the line of the nuclei. Both orbitals are in pi molecular orbitals. So if I take a p orbital and I make a molecular orbital out of it, we're going to call this a pi orbital. Right? And you'll notice that there is some similarity happening between the terminology we used for our valence bond and our molecular orbitals. Right? So our bonding, we're going to call that a pi orbital, and our anti-bonding will be a pi starred. Right? And this little 2p is saying where those came from. Right? So here we're going to look at molecular orbital theory for a more complex molecule. All right? And we've got a couple of different orientations for them, depending on which atoms or which diatomic atoms you're looking at. We've got 2 different conformations, but they're still going to follow that same rule. We're going to do electron 1, electron 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then you can figure out the bond order, like am I in a anti-bonding or am I in a bonding one, okay? I will give you these on a test, right? So I will give you these. I would expect that if you have oxygen and each is coming in with 6 electrons, can you put 12 electrons into the box, right? So can you do this, right? So here we've got 2, 4, 6, 8, 10. This would be something like neon, right? So this is our configuration for neon. We've got 10 electrons. They're all going to fill themselves into these boxes. As you continue on, you can add more electrons. They're still going to follow the same rules with Pauli exclusion principle, where they can't have the same 2 electrons in the same space at the same time. And they're still going to follow Hund's rule, where they're going to do unpaired spin-up electrons first. Right, so looking at what's happening with these, and we're talking about some of these p orbitals. So if I've got a p orbital, I can combine it with another p orbital, and I can make a bonding orbital where we've got constructive interference. Now remember back when I was like, okay, you've got these wave functions, right? And they've got positive parts and negative parts, and we have to do the square to get the probability, right? Well, sometimes you will see lobes that are labeled with pluses or with minuses on them. And that's just saying what part of the wave function it is. It's not saying what the electron probability is, right? It's just that this is the wave function from the positive part of that wave, and this is the negative part of that wave, right? You're squaring it to find the probability so the negative goes away. But if I take the positive part of one wave function and the positive part of another wave function, I take a positive and a positive, I put them together, I'm going to end up with a big positive. That's going to be my bonding orbital. So this is a sigma to p. Right, it's a bonding orbital that's coming from a p orbital, an overlap of a p orbital. I've got my anti-bonding orbital, where I'm going to take the plus lobe and the minus lobe of p and try to do end-to-end overlap with them. Right, if I got a plus and a minus, they cancel each other out. I get a node in between with no electron density. Right, I've reduced the electron density over here, and I've maintained it over here. So I've got very little electron density between my two nuclei. Right? In our end-to-end sideways combination of our p orbitals, we're going to end up with our pi orbitals. Right? So remember, we can do this end-to-end, or we can do it in parallel. If we're doing it in parallel, right, I'm going to take my py's, right, and I can overlap them. If I add them up, I'm going to end up with a shape that looks like this. And that should look really familiar from your pi bonds. Right? If I do the difference, I'm going to get a pi starred, right? And I'm going to end up with a node in between my two nuclei, right? They're not sharing electron density, right? This node says no electrons in here. And this, lots of overlap, says, yeah, we're doing a lot of sharing. And we can either do this in X or we can do this in Y. It's the same thing, you're just rotating it on the axis. Let's take a quick discussion into orbital theory and explaining diamagnetic versus paramagnetic. All right, so if we take oxygen, that O2, by itself, all of our electrons, we got two definitions. One is diamagnetic, which means all our electrons are spin paired. That's going to be something that is weakly repelled by a magnetic field. Something that is paramagnetic has one unpaired electron. So it is something that is going to be weakly attracted by a magnetic field. Oxygen, O2, is predicted to be diamagnetic based on its electron dot structures and valence bond theory. However, experiment shows that it actually is paramagnetic. It's going to have some response in a magnetic field. It's going to be slightly attracted to a magnetic field. And you can do an experiment where you try to pour oxygen down between some really strong magnets. These magnets are going to align those electron spins. Right? And so valence bond theory doesn't do a good job explaining that. Lewis structure doesn't explain that. We observe this behavior. It is going to be explained by molecular orbital theory. Right? So for our O2 molecule, when we put it into its little Plinko box here, right, where we've combined our atomic orbitals, we're going to have our sigma bond that's coming from our s orbital, then our anti-bonding from our s orbital, then we're going to have a sigma bond from our p orbital, right? And then we'll have our pi bond from our p orbital, and then we'll have our pi starred, our anti-bonding pi orbital, and then our anti-bonding sigma orbital. That's going to have the highest energy. So like, notice that symmetry that's happening here. Right? We're still going to conserve the number of orbitals. We're just changing their energy a little bit, and we're saying that the electron's going to be shared. So when I fill this guy out, right, and I put all of my oxygen electrons in there, I'm going to end up with some unpaired electrons in its degenerate pi starred 2p orbitals, and it's therefore going to be paramagnetic. If I look at fluorine, right, difluorine, right, it's going to have two more electrons, right, this guy and this guy. They're all paired. There's no unpaired electrons to align with that magnetic field. Right, same thing with nitrogen over here, right? Nitrogen has all of its electrons paired. If we could get something that had one more electron in between, like like O2 plus, right? We could put another electron up in here, and that would be, excuse me, that would be paramagnetic. So magnetic. Talk about insane clown posse. Magnets. How do they work? Unpaired electron spin. That's how they work. So looking at our molecular orbital, let's do an example. We're going to use our molecular orbital model to predict the bond order and magnetism of the following two molecules, dineon and diphosphorus. So in dineon, the valence orbitals of neon are s and p. We're going to construct the molecular orbital structure. The neon 2 molecule has 16 valence electrons, 8 coming from each atom. Placing these electrons into the appropriate molecular orbitals is going to give us this diagram. So 2, 4, 6, 8, 10, 12, 14, 16, right? The bond order, we've got this, we're looking at this, it's all unpaired, it's all paired, right? So we don't have any lone pair electrons to make it magnetic. If we look at the bond order, right, so we've got 2, 4, 6, 8 antibonding, and then we've got 2, 4, 6, 8 bonding. So it'll be 8 minus 8 over 2, so 0 halves, 0, any 2 does not exist, right? Your bond order has to be a number that is positive, bigger than 0. Right. Let's look at our diphosphorus. That's going to contain phosphorus atoms, and they're going to come from the third row of the periodic table. We're going to assume that diatomic molecules of period 3 elements can be treated just the way we've done it so far. We're going to draw the MO diagram. That's going to be the same as that for N2. We're going to assume that they're in the same column. They're going to call them the same way. The only change will be that the molecular orbitals will be formed from 3s and 3p atomic orbitals instead, and that those inner shell electrons are not doing anything. The P2 molecule has got 10 valence electrons, 5 coming from each phosphorus atom. So if we get our structure like this, right, and again, remember, I will give you these structures. We're going to put in our 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? The molecule is going to have a bond order of 3. And so we look at all the guys in antibonding. Right? We've got these guys that are in antibonding. And then we look at all the guys that are in bonding orbitals. So we got 2, 4, 6, 8. So we'll have 8 minus 2 over 2. So we're going to have 6 over 2, which is equal to 3, which is bigger than 0. So it's expected to exist and be diamagnetic because they're all paired. Heteronuclear diatomic molecules are composed of 2 different atoms. They can also involve, in special cases, molecules. Certain atoms are adjacent to each other on the periodic table. They are going to be best described by this MO model. So if you look at HF molecule and assume that fluorine uses only its 2p orbitals to bond to hydrogen, the molecular orbitals for hydrogen fluoride are going to be composed of the fluorine 2p and hydrogen 1s orbitals. Right? So just like we saw where we had the hydrogen with its kind of s orbital over here, and then we had fluorine where we had an unfilled P, right? And then we had some filled guys on our other axes. Right? These guys were going to form that sigma bond. Right? The fluorine 2p orbital is lower in energy than hydrogen 1s orbital. The sigma molecular orbital holding the binding electron pairs should show a higher electron probability closer to the fluorine, and our electron pairs are not going to be equally shared. So let's take a look at what that looks like. So here it's a little bit more complex. Right? We've got the hydrogen 1s as being higher in energy than the fluorine 2p, right? But we're still going to end up with a sigma bonding and a sigma antibonding orbital. Right? If we look at the probability distribution, we've got our hydrogen nucleus and we've got our fluorine nucleus. And you notice that the electron density is a lot higher around this fluorine than it is around the hydrogen. Right? So you would expect if it was evenly shared, right down the middle, right? You would expect that to be even. Stevens, it's not. It's going to be a little bit more over towards the fluorine because the fluorine's more electronegative. We can use the molecular orbital theory to predict the magnetism and bond order for the NO plus and CN minus ions, right? So these are actual ions that exist. They're not made up ones like helium-2 or H2 minus or something. So our NO plus 1 cation has 10 valence electrons, right? We're going to come in with 5 from the nitrogen, 6 from the oxygen. We're going to lose 1 because it's a plus 1. Our cyanide ion is going to have 10 valence electrons, 4 from the carbon, 5 from the nitrogen, and 1 extra. Both ions are going to be diamagnetic, and they're going to have a bond order derived from our equation where we've got 8 minus 2 over 2 is 3. So these are both ions that are going to exist. Right? The molecular orbital diagram for these is the same, right? So here we've got our bonding orbitals, right? They can either be a sigma or they can be a pi, right? Or we can have antibonding orbitals, right? Some of them are going to end up going into the antibonding orbitals. Right? 2 of them are going to go into here, right? We can compute both the bond order and we look to see whether these guys are the same or not. So they're isoelectronic. They're going to follow the same pattern, the same filling pattern. They got the same number of electrons. They're going to look the same when you plot this out. Right? Ideal bonding model should contain the following: simplicity of a localized electron, delocalization features of the molecular orbital, and combining both models is going to help us describe molecules that require resonance. You can think of the sigma bond as being localized and the pi bond as being treated as localized. So we thought about all those sigma and pi bonds as localized on one spot. They're bonds in which the sigma and pi bonding electrons are associated with only 2 atoms. For our resonance molecules, when we're drawing our Lewis structures, they require delocalized bonding when applying the valence electrons. So those Lewis models with resonance are already talking about something that's like a molecular orbital, where those electrons are shared throughout the entire atom. So our delocalized bonds are ones in which the pi bonding electrons are associated with more than 1 atom. So for example, nitrate, NO3, carbonate, CO3, 2 minus, benzene, ozone. Right, so in benzene, we've got our benzene ring here where we've got this alternating single, double, single, double, single, double. We could draw it the other way was a double, single, double, single, double, single. We've got a resonance structure for that. Looking at our carbons, these are going to be sp2 hybridized, right? So it's going to be sp2 because I've got 3 things. I'm going to need 3 orbitals. It'll be sp2 hybridized. Right, so we're going to take some of our carbon. We're going to hybridize 3 of our orbitals to get some sp2 hybrids. Right, we will have some left. So this is going to be our sigma bonds, right, between carbon and a carbon and a carbon and a carbon, and also between the carbons and the hydrogens. Right, so we're going to form our backbone structure using our sigma bonds. Right, we've got this leftover p, right, that can do some pi orbitals, but now we're going to delocalize this pi orbital across the entire thing because we can alternate that structure. Right? And that's the end of this chapter.